All right, class, welcome. Today we're going to run through a little conceptual exam. Now, the topic might sound like something from a 100-year-old textbook, but it's actually one of the most powerful tools we have for building our future. The subject? Thermodynamics. So let's get started.
So, right off the bat, here's the big question for today's exam. Could a science that's literally from the age of steam engines really hold the key to a sustainable future? It's a totally fair question. And the answer, as you're about to see, is a huge, resounding yes. Let's dig into why.
Okay, first question on the test. This one's about the fundamentals. What are the non-negotiable, absolute laws of the universe that govern every single bit of energy transfer? We're talking everything from a star exploding down to you just brewing your morning coffee.
So here they are, the two big rules of the game. The first law, you've probably heard of it. Energy is always conserved. It's all about quantity. But the second law, now that is the real game changer. It's all about quality. And what it says is that every single time you convert energy, its usefulness gets a little bit worse. It becomes more disorganized, a state we call increased entropy.
And let's be super clear here. This isn't some design flaw we can just engineer our way out of. No, this is a fundamental rule of physics. The second law is the reason a 100% efficient engine is pure fantasy. There will always be waste heat. And understanding this cosmic speed limit is step one to using our energy resources wisely.
All right, on to question 2. If that first question laid out the rules of the game, this one is all about strategy. How do we actually measure the quality of energy, not just how much of it there is?
And this slide right here shows you the key difference. On one side you have energy. That's the total amount. Think of it like a giant, calm lake. But on the other side, you've got exergy, and that is the useful part. It's like the powerful waterfall flowing out of the lake that can actually get stuff done. When we're talking sustainability, our goal isn't just to manage the lake, it's to preserve the awesome power of that waterfall.
So to put a formal definition on it, exergy is the measure of an energy source's quality. High temperature heat from the sun or electricity from the grid, that has super high exergy. That lukewarm waste heat coming off the back of a power plant, very, very low exergy. And this really clarifies the true goal of efficiency. It's not just about saving energy, it's about preserving exergy.
And this brings us right back to those fundamental rules we talked about. There's this thing called the GUIs to DOLA expression, and it proves a direct link. Destroying exergy is the exact same thing as creating entropy. So think about that. Every time we're inefficient, we're not just being wasteful, we are actively creating more disorder in the universe. It's literally a force for chaos.
Okay, you're all doing great, but enough with the theory. For question 3 of our exam, let's get practical. Let's look at some case studies. How do engineers actually use this idea of exergy analysis to solve real-world problems?
First case study, a power plant. Now, a standard efficiency metric will tell you how much energy is lost overall, but exergy analysis, it's like a thermal magnifying glass. It pinpoints the exact spots where the highest quality energy is being destroyed, and it's often right at the beginning, during combustion. This tells engineers precisely where to focus their efforts to get the biggest bang for their buck.
Another great example is in systems like heat pumps. The most efficient ones are what we call highly reversible. This basically means they can run forwards to heat your home or backwards to cool it with the absolute minimum energy loss and entropy creation. In the world of thermodynamics, reversibility is the gold standard of efficiency. It's basically the A+ on this exam.
Now, thermodynamics can also throw some pretty surprising and honestly kind of worrying insights at us. Take this quote from the source material. It's about nanoparticles, and it warns that if we spread materials too thin in our waste, the exergy, that useful energy it would take to recover them, could become greater than what it takes to just mine brand new ore. It's a really stark reminder that recycling isn't some magic bullet. Designing things to prevent that kind of dilution in the first place is just as important.
Excellent work so far, everybody. Now for our fourth and final graded question. Let's zoom all the way out. How do these super precise engineering principles connect to the huge global challenge of sustainable development?
I'm sure we've all heard this classic definition before. It's really powerful, right? But it can also be kind of vague. I mean, what are needs? How far into the future do we have to plan? Well, thermodynamics gives us a way to make this concrete. True sustainable development is all about preserving the Earth's exergy for future generations.
And this isn't just a cool theory, it directly informs goals like these from the UN. When you talk about achieving clean energy, or building sustainable cities, or taking climate action, you are fundamentally talking about a thermodynamic challenge. It's all about getting the most useful work, the most exergy, out of our resources while creating the least amount of waste and disorder. Thermodynamics is basically the scientific roadmap for hitting these critical goals.
Okay, you've made it to the final exam. For this one, you can put your pencils down. This last question, it isn't about physics or chemistry. It's a question about us. To frame this final challenge, I want you to consider this incredible distinction in the Indonesian language. They have two different words for we. There's kami, which is an exclusive we. It means my group, my friends, but not you. And then there's kita. That's an inclusive we. It means all of us together in this.
So, here it is, the final question on our exam. When we talk about sustainability, when we say we need to act, which we are we actually talking about? Are we using kami, expecting some other group, some other country, maybe some other generation to solve the problem for us? Or are we finally ready to embrace kita and recognize that we includes every single one of us? Thermodynamics gives us the scientific tools, but answering that question, well, that's the test for all of us. Class dismissed.